Hello, we are back with area moments of inertia and with the parallel axis theorem. The purpose of this tutorial is to show you how to apply the parallel axis theorem to calculate the area moment of inertia of a composite area. A composite area is a rather complex looking area that is nevertheless composed of multiple simple partial areas. For example, if we have a body or an area like this, at the first sight it actually seems to look rather complex, but if you look closely, you will see that this area is composed of three partial rectangles. One rectangle that is here, the second rectangle that is vertical, and this small rectangle. And to calculate the area moment of inertia of an area like this with respect to a given reference axis, you need to use this set of formulas. Basically, to calculate the area moment of inertia with respect to the y' axis, you would have to add the area moments of inertia of all three individual partial rectangles together. And in this case, what you would need to do is to start computing the area moment of inertia of the first partial rectangle with respect to the reference coordinate system or the reference axis, which for this formula is y', and then you would compute the area moment of inertia of the second partial rectangle and then of the third partial rectangle, and in the end you need to add the area moments of inertia of the partial rectangles together. Let me start working out the mathematics. We're going to compute the area moment of inertia of the first partial rectangle. That partial rectangle will be labeled as A1, the second as A2, and the third one as A3. That's just for a better overview. And the area moment of inertia of the rectangle A1 will be labeled as I sub y' A1. Okay, and that is equal to z' sub cg squared. Now, this term, z' sub cg, that is the distance between the centroid of the partial rectangle 1 and the reference axis along the z' axis. So z' sub cg, as I said, that's the difference along the z' axis between the centroid of the first partial rectangle and the centroid of the second partial rectangle, or the y' axis, because the y' axis intersects with the centroid of the second partial rectangle. And that distance needs to be determined so that we can plug it into the formula. That distance on the sketch is this, and if you look closely at the geometry of the whole body, you will see that the distance between centroid 1 and centroid 2 along the z' axis, or any axis that is parallel to z', is simply b plus a half. Why? Because the height of the second partial rectangle is 2b, so the distance between the centroid and the top is just b, and then in the first partial rectangle we have the height from the bottom of the rectangle to the centroid as a over 2. And therefore z prime sub cg1, I'm putting a 1 here because I'm referring to the first partial area, and that distance is, if you are very strict about your signs, you would actually have to use a negative sign, because that distance extends into the negative z prime axis. So it's gonna be minus b plus a over half. I said you have to put a minus if you are very strict when it comes to algebraic signs, but if you don't do it, don't worry, because that distance will be squared anyway and the minus sign will disappear. So in this regard, I will omit the negative sign and directly put the positive value. So we're looking at this formula for the first partial rectangle. So z prime cg1 squared would be b plus a half squared times a, the area of the first partial rectangle, and that is just a piece of cake. It's 2b times a, so nothing to worry about. 2b times a, and this term I sub yi, that is the area moment of inertia of the first partial rectangle, given that the reference axis is the centroidal axis, as we discussed in the first video of this series. And that value can be obtained from tables, but if you have watched the first video, you know that to calculate the area moment of inertia of a rectangle where the reference axis is the centroidal axis, you have to do, let me write it down here, I sub, well, let me just write down y1, just to indicate that we're dealing with an axis that is the centroidal axis of the first partial rectangle. And hopefully you know that you have to multiply 1/12 and then attach the third power to the length that is perpendicular to the centroidal reference axis. So in our case, let me just briefly indicate the centroidal axis. That would be this one, with I1 and Z1, just for convenience. And if you have an axis like this and you want to calculate the area moment of inertia of a rectangle, you have to attach the third power to the length that is perpendicular to the reference axis. In our case, A would be perpendicular to y1, and the third power would be attached to A, while the length that is parallel to the centroidal reference axis, the length is 2b, and you just attach, you don't change the powers, you just treat it as the first power. So it's going to be 2b to the first power. And we need to add this term to this equation. Actually, I'm gonna write it out without the bracket. Okay, so that's the term for I sub y prime for the first partial rectangle. And if we expand this equation, we're gonna have to apply the binomial theorem on this term, which will give us b squared plus ba plus a squared divided by 4 times 2b times a plus, because 1/12 is multiplied by 2, we only have 1/6. So 1/6 a to the third power times b. And now be with me and follow the algebra. Let me summarize some common terms. So we have 2 times a times b to the third power plus 2b squared times a squared plus 1/2 a to the third power times b plus 1/6 a to the third power times b. And that expression can be simplified into 2a times b to the third power plus 2b squared a squared plus 2/3 times a to the third power times b. So, and that's the area moment of inertia of the first partial rectangle with respect to the y prime axis. You should know that this is not yet what we're looking for. We're looking for I sub y prime, but we've just determined I sub y prime for a1. Now comes I sub y prime for a2. And this is going to be much shorter than for a1 because the reference axis, which is the y prime axis, that's a centroidal axis. So if we apply this formula, we actually can omit this term that pertains to the parallel axis theorem. So the z prime cg2 squared times a, we can omit this term because, again, the reference axis is the centroidal axis that runs through the centroid. So we only need to take into account the I sub y, y2. And the formula okay, as you know, you attach the third power to the length that is perpendicular to the reference axis. In our case, that length would be 2b. So you adopt the 1/12 from above, and then the length that is perpendicular to y prime, that's 2b, and 2b needs to be powered to up to 3. Okay, and the length that is parallel to the y prime axis would be a for the second partial area. So times a, and we can just leave it as it is. Well, actually we can do some simplification. 1/12 times 8 times b to the third power times a, and 2 to the third power is equal to 8, and that is equal to 2/3 b to the third power times a. And at last, let us calculate the area moment of inertia of the third partial rectangle, A3. And that is, let me find some space. Okay, I'm gonna continue here. So I sub y prime of A3 is equal to, okay, now we have to apply the same method that we did with the first partial rectangle. Okay, let's identify the distance between the centroids of the two partial rectangles along the z prime axis, and that distance is basically just, let's see, okay, that distance is, let me label it. That distance is here, and it can be computed as z prime cg3. Okay, the distance between the centroid of partial area 2 and its bottom is b, and you have to subtract half of the height of the third partial rectangle to arrive at z prime cg3. b minus a over half, and even if you're very picky about the algebraic sign, it's going to be positive because the distance extends in the positive z prime direction. Okay, let's plug in b minus a half to the third power. No, sorry, not to the third power. It should be squared. Okay, sorry, I'm just thinking a little bit ahead. The third powers will follow a little later. For now, you have to square this term times the area of the third partial rectangle, and that's just a times b. Plus, again, if you apply the insights that we talked about as far as the area moment of inertia with respect to a centroidal axis, you will get 1/12 times a to the third power. A is perpendicular to y prime times b. And at this point, I will not write out the whole algebra. I'm gonna make a shortcut to, not make this video too long. I will write down the final result for I sub y prime of A3, and that is equal to minus 1/6 a squared b. No, sorry, not squared, it's the third power this time. Okay, a to the third power times b minus a squared times b squared plus a times b to the third power. So that is the equation for the area moment of inertia of A3. And finally, we can sum up these three equations to arrive at the area moment of inertia of the composite area with respect to y prime. So I sub y prime, the y, I want it to look good, is equal to I sub y prime. Okay, I should not worry too much about the aesthetics of the y's. A1 A2 A3, that is equal to 2a times b to the third power. I know it's rather dull and tedious to watch carrying out the expansion and the addition, but just be patient for one more time. We are almost at the finish line. Okay, sorry, I'm gonna put the letters in order. Okay, and if we simplify this long term, we are gonna get 11/3 times a times b to the third power plus a squared b squared times plus 1/2 times a to the third power times b. All right, finally we have arrived at the final value for I sub y prime, and that's the area moment of inertia of the composite area with respect to y prime. If you wanted to do the calculation on I sub z prime, you would do analogous steps. Don't worry, I'm not going to do the math here because I have spent more than enough time calculating I sub y prime. But I hope that the patience has paid off and that you have learned how to calculate the area moment of inertia of a composite area.